Okay, so we're ready to do some more calculations. Here's another calculation with the sample mean. It says about how large must n be so that the probability that x bar exceeds 101 is less than 0.01. That's kind of a backwards calculation. What we're thinking is, if we looked at x bar's distribution like this, we'd want to be way out here, so that probability of being bigger than whatever the... Here's 101 sitting here. We pick an n. Making n larger makes the distribution narrower, so as you increase the size of n, eventually this tail gets squeezed down to be basically nothing. So if we take a large enough n, we can get that probability less than 0.01. So here we're going to need to find a z whose probability is 0.99 in the tables, because in this picture here it's 0.99 sitting on that side, and the tables list the less than probability. If we go to the tables, we find a z of 2.33 corresponds to that position. So we take the z formula, we put 2.33 here, we put 101 for x bar, we put 100 for mu, we put 2.6 for sigma. We're trying to solve for n, so we put n in there. And then we rewrite that as 2.33 is root n over 2.6. That's a 1 up here. And solve it by n by multiplying by 2.6 and squaring both sides, and getting 36.70. Now you can't have a sample size of 36.7 because it has to be a whole number. If I use 36, it hasn't quite squeezed the distribution close enough to 100 to get that tail probability to be less than 0.01. So 36 is not quite big enough, but 37 will just make the probability slightly less than 0.01. We want it to be less than 0.01, not greater than 0.01, so we always use the next larger whole number if we're trying to achieve a goal of making a probability, a tail probability, small. When we solve for n, if we get a fraction there, like 36.1, we'd also use 37 as the sample size. Okay, so that's our warm-up calculations for x bar. And then we're going to talk about statistical inference, which is what we're going to start doing. So statistical inference is drawing conclusions about a population by using a sample. And then we have a test statistic ordinarily that we are looking at. We can think of the sample mean as being our test statistic. We use x bar, something we compute from data, to draw conclusions about mu, a characteristic of the population. So in order to get started, we have to make some assumptions. So we say our first steps in this process is we're going to assume the population is normally distributed. We'll be able to weaken that assumption later on. We're going to assume we're sampling by simple random sampling. All the calculations we do for x bar are only valid if the sampling technique is simple random sampling. So if you have some other kind of sampling technique you're doing, the estimate for the standard deviation won't be correct. And you need to consult with an expert about how to handle the situation. 3, sigma has to be known. Ordinarily you don't know sigma, but we're going to assume for now, which is first steps, our assumptions are we know sigma. Sometimes you have a guess about what sigma might be, based on your experience with that kind of population in the past. And 4, a more delicate situation, the population size is large compared to the sample size. Ordinarily your sample is pretty small compared to the population, and so that's not an issue, but sometimes if you're sampling, say you're sampling from our class, and you sample 10 people out of the 28 in our class, we wouldn't say the sample size is small compared to the population size. And what that does, if the sample size is large, is the amount of variability is decreased, but we're not going to talk about that situation. We're just going to assume in situations where you're doing sampling that the population is pretty big and your sample is small compared to the population size, like at least 1/10 of the population size. Okay, so those are our first steps. We're going to move on to talking about confidence intervals based on these things being in place as we move forward. Here we go.